Mathematical modeling, logistic population model. Some reminders of the Malthusian population model before this. The Malthusian is simplistic, but it is a start. Modeling has to work in theory, and they go from simple to rather complex models which can only be handled by computers. A reminder about the Malthusian model. First of all, if there's no external influence, a population will increase in a geometric ratio, multiplying by a factor every time to obtain the next time period. Food supply, however, increases only in an arithmetic pattern, in other words, adding a term on each time. At some stage, the population is going to exceed that's sustainable by the food supply, because a geometric pattern will always overtake an arithmetic pattern, and the population collapses. Once the population has dropped to a stage at which its number can be sustained again, the population number will begin to grow again. There's what is likely to be the graph of a population of lemmings over a number of time periods by the Malthusian population model. Climbing, then collapsing, and then climbing again. More realistically, that's what's likely to happen. There are going to be certain influences like diseases, like there must have been a disease at this stage. There must have been something quite serious happened here, where the population didn't recover for a long time. And there are other external factors, such as competition from other populations, predators, disease, rainfall, floods, droughts, and so on. So, while the Malthusian population model doesn't take into account that the rate may change as the population changes, in other words, the consumption of food increases, so that becomes a problem in its own way for the increase of the population, a modification is needed. Now, if you consider these three populations here, you'll see that they start off just the same as a Malthusian type of population, but then they seem to level off and flatten out. We need to take into account that population growth rate is likely to decrease as population grows. Not the population number is likely to decrease, but the growth rate is likely to decrease due to the limitation features of the larger population. So, there's the Malthusian versus what we're now going to look at is the logistic model. These cases where it seems to level out. So the Malthusian grows with a collapse, grows exponentially with a collapse. The logistic seems to flatten out after a while, after a time. So let's have a look at the logistic population model. It works the principle that the place of abode of the population has a carrying capacity or equilibrium point beyond which the population cannot grow. Gets to a stage, and after that the food will not sustain any greater numbers. And it's a characteristic S-shaped graph. Carrying capacity is represented by the asymptote of this graph. There. So at this stage, the growth rate is increasing. And then at that stage, decreasing. And there, at the point of inflection, is the maximum sustainable yield, where you'll see that this graph is increasing the most, and then it starts increasing less again, determined by its gradient. So, while in the Malthusian model the rate of change of the population number is constant, the rate now changes as the population grows in the logistic model. It's influenced by the carrying capacity of the environment, the number that the environment can hold. The closer the population approaches the carrying capacity, the lower the rate of change will be. So we could write the rate of change as delta P over P, the change in population number over the actual population. That's the rate of change. And it's going to decrease. Pretty logical it's going to decrease because this population number is increasing. And if the denominator of a fraction is increasing, the fraction is likely to decrease unless the actual numerator can match the denominator. R is still the growth rate, same as in the Malthusian model, but now it's referred to as the intrinsic growth rate. Because it really does depend on the density of the population. And in fact, it's only the maximum growth rate. It's the growth rate at the start. So, here's a graph of growth rate versus population. As the population increases, this is the growth rate of the population. You'll notice it starts at R and immediately it's decreasing. And it's a linear decrease, straight line decrease, until the growth rate ends up as 0. That's when the graph flattens, and it's virtually flattens, and it's asymptotic to the level of the sustainable yield. And when R is 0, there is the carrying capacity of the environment. So if we talk about the graph, R is the maximum, population growth rate 0 at the carrying capacity, and if we're given that graph, these are the x and y intercepts of that graph. Let's find the equation of this straight line here, because if you look at it, we have the y-intercept, we have the x-intercept, and those alone should give us the equation of the line. Well, they will. P is the x. So we're not going to talk about x, we're going to talk about p. We're not going to talk about y, we'll talk about delta p over p. The gradient of the line, well, the line goes from 0r to k0, so we're going to use our formula y2 minus y1 over x2 minus x1, and we obtain the gradient of negative r over k. And the y-intercept is r. So now, there's the equation of the straight line, y equals mx plus c, and we're now going to substitute those values in. Now what follows is a bit of algebra. We have a common factor of r, which we're going to take out. Now we want to know delta p on its own, and this is delta p over p, so let's multiply through by p. And delta p equals, and we're going to end up with rp, p multiplies outside there, into 1 minus p over k. Now, the idea of model is to be able to predict the number in the next time period. So, Pn plus 1. Now, Pn plus 1 is equal to Pn plus the change in population. Pn plus 1 equals Pn plus delta P. Well, there's delta P. So therefore I can put that in place of delta P, and we have what is the formula for the logistic population model. That's known as the logistic formula. Or the logistic function. Some of the context for a good model: biological population growth in a species living in an ecosystem with a limited carrying capacity. That's generally what we talk about most of the time. The spread of a non-deadly virus in a human body. Deadly, well, there'd be no human body left. Living body. Spread of information within societies. It's interesting. The growth of a number of hits on a website. That's not as predictable, but that does produce a good model. And the sales of a new product over time. That's pretty logical, that the new product, at first the growth rate of sales is going to be greater, and then slowly it'll tail off as the number of people who still don't have that product is not increasing as much. Right, an example. The population of 5 spotted genets grows logistically at a rate of 35% per annum in a city suburb that has a carrying capacity of 500 genets. Now this assumes that no extermination is done, and there are no other predators or anything to affect it, or disease. So it's just purely the genets and the food. How much has the value of P grown over the following time period? So from 1 to 10, and then 11 to 20, and so on. Well, P0 is 5. We apply our formula. It's color-coded within the question to the formula, and that can indicate our substitution. Notice that Pn is substituted 3 times. For P2, we now use this value of 6.73 in the formula to obtain the next one. And so we go on through to P10. This, same as the Malthusian, is a discrete model, so each value needs to be calculated. And that makes Excel very useful for that. Notice, for example, here, to find that growth rate, I subtract the value at 10 from the value at 20. That'll give me my 10 years. Here you'll see that it's pretty much reached it. These will obviously differ to a number of decimal places because it's asymptotic, so it'll never actually reach the 500, but it's getting pretty close. And see, the growth is only 1 in 10 years. Draw a graph by plotting points. Okay, so we're going to draw a graph of the values from 1 to 30, and that's what it gives us. The S-shaped curve. Discuss the increase over the 3 intervals in question 1. So there are the 3 intervals, there they indicated there. Well, the first one, it's initially slow due to low breeding numbers. Then that's a time of great increase, rapidly increase in the middle period when there's still plenty of food. But notice that it's starting to slow down there. And the final period slowing down to a constant as the environment limits growth. At what stage is the growth at a maximum? There we are. At that point there, it's the greatest gradient to the graph. It's the point of inflection, end of the 15th time period. Let's have a look at a new example. This one, the purpose to lead you through the process of testing a set of data to see if a logistic equation can model the data. That's quite necessary in mathematical modeling, to be able to test the data to see in fact whether it will fit a model in the first place. And then finding the logistic equation to model the set of data. So here we have the US census data up to 1940. From 1790, every 10 years. Number of questions which we'll deal one at a time. Question 1 says indicate. Notice here the question is best answered using a spreadsheet as usual because this is discrete. Index the years with 1790 as the 0 year. Well, all that means is that's 0, so therefore that one will be 10 because it's 10 years on. So there, the indexing there, it makes it easier to apply in formulae, and there's the populations coming straight off the table. Calculate delta P, the change of rate of population for each time period. Now, in order to calculate a change in a time period, it's like the average gradient. So to find the rate of change in this time period, what I'm going to do is I'm going to go to either side and find the average of those two. Pn plus 1 minus Pn minus 1 over time interval. And the average between those two, there's been a 20-year gap, so I'm going to divide by 20. So it's 7.24 minus 3.93 over 20. Note that this means we cannot find the rate of change in the time period at the beginning or at the end. And there are the rates of change. Remember that we're investigating still whether this would fit a logistic model, so we're going to test delta P over P versus the time periods. Right, so there, plot the values of delta P over P against P on the scatter graph. So delta P over P, there we calculate it, the division. There is our scatter plot. Determine the equation of the best fit line for the graph in question 3. Well, the easiest way to do that is to take each point and substitute it into a calculator, enter it into a calculator, and use the calculator with the regression line process. Does it fit the shape, first of all? Yes, it's reasonable. It fits a pretty good straight line. There goes the straight line. That is the actual regression line, and it definitely looks like a least squares regression line. Using linear regression on the calculator, that's why I can get to so many decimal places. There is the equation of that line. Determine the value of the parameters r and k for the logistic equation. Well, remember, those are simply the y and x intercepts. So the y-intercept, 0.0354, so that's the rate at the start, and k, 232, so there's the carrying capacity of the USA, according to this model, 232 million. Plot the population of the USA against the indexed years. So in other words, it's the population against these years. Here it is. And it seems to be forming. I think if this goes further, it's likely that it's going to actually flatten out there, yes. Looks a bit like an ogive curve too. Compare the results of the logistic equation to the actual census data between 1790 and 1940. Are these numbers realistic, and why? Now the calculation can be done by Excel or calculation, but remember that you have to enter PN 45 times, 3 times per formula, 15 times. So it's better to put it onto the formula into Excel and do it that way, which I have done. And there's the modeled population. That's what it models by the formula. Are they realistic? Well, if we have a look here, pretty good, pretty good, pretty good. Still okay, but now it's starting to drop, starting to lag behind somewhat. So initially it appears to model the census data fairly realistically, though it starts to underestimate from 1850 onwards. Use the logistic equation to predict the USA population in 1990. The census results from 1990 indicate a population of 248.71 million. Is this model still useful? So I'm going to take the actual census population here, and I'm going to now model it year by year through to 1990. And using the formula, there it is there, 1940 to 1990, that's the actual in 1940. Now I'm using the model, and I end up with 135.05, very far off the actual. So in fact, the model is no longer useful at that stage. There are other factors involved. Pretty clearly there are. In fact, if you think about it, medical science advancements, all sorts of things, nutrition. So that's why the actual carrying capacity of the environment has increased considerably since 1790. A summary. Testing for logistic behavior. We calculate the value of delta P over P for each value of n, excluding the first and last, because we can't work out delta P for the first and last. Plot these ratios against the corresponding function values Pn on the graph. If the graph is roughly linear, then a logistic model is suitable. So we get that graph going through from R down to K. Estimate the parameters R and K. Well, this is just straight algebra. Fit a best fit line to the plotted points. The best way to do that is entering on a calculator or doing it on Excel. You can estimate it too by drawing what you look to think is the best fit line and choosing 2 points on that line, and finally the equation the normal algebraic way. C gives the value of R, and value of K is the y-intercept, in other words, the x-intercept, value of K is the x-intercept, in other words, y0, and if you solve 0 equals mx plus c, we end up with negative c over m.